All right, so let's go into our first addition reaction, hydrohalogenation. So in this case, the hydro stands for hydrogen. The halogenation stands for some kind of halogen, so we'll call that X. In this case, it's going to be chlorine, bromine, or iodine. We don't use fluorine too much. And so what we're going to do is we're going to add hydrogen and X across our double bond. And so if we think about this reaction, right, we're doing an addition reaction. So generally these things are done at lower temperatures, in this case, negative 30 degrees Celsius. That way we form this addition, right? Our enthalpy is going to dominate. And you can see when we add HBr across this reaction, we add some HBr. And so let's think about the mechanism here. The first step here is going to be attack by our pi bond. And this is going to be the rate determining step. So this is going to be the most important step. And so our pi bond is going to attack the hydrogen of our HBr, right? The positive, partially positive side of things to form a carbocation. And then in our second step, we have the attack by the nucleophile, in this case, our halide. To give us our final product where we've added HBr across the compound. And so let's think about some things. Let's think about the Regio chemistry of this reaction. Right, so we're thinking about adding HX across this bond, and so we could come up with kind of one of two products, right? We could add this X to the carbon on the right, or we could add it to the one on the left, right? Which one of these is going to be preferred? Well, if we want to know what's going to happen, we should think about our mechanism. So let's go ahead and take a look at our mechanism. And so again, the first thing we're going to do is use our pi bond to attack our hydrogen. And so we could form one of two intermediates here. We could add the hydrogen on the left and then have the carbocation on the right, or vice versa, right? And so if we think about our carbocations, this one's tertiary, that's relatively stable. And this one's primary, that's a big no-no, right? So that one cannot happen. And so then if we think about our X minus then coming in, it'll go to this more substituted position. And so our product will be the one on the right and not the one on the left. And so this is what's known as a Markovnikov addition. Named after the guy who discovered it. And so there's different ways, if you read about Markovnikov additions, there's different ways it can be described. Some say that the hydrogen goes on the less substituted carbon, or that the X goes on the more substituted carbon. What I always like to think about is that the more stable carbocation will be formed. Right, and so the carbocation will go on the more substituted one, and then your nucleophile will attack that carbocation and then go on the more substituted side as well. If we think about the stereochemistry here, we have a carbocation intermediate. So for example, we'd have something like this. And remember, this is going to be totally planar. And so your nucleophile can come from either side. And so even if you had some kind of stereochemistry before, you will not have anything after, because you'll racemize the whole thing. You get a racemic mixture of products, right? That's one of the downsides of using these carbocation intermediates. Another downside of using these carbocation intermediates is rearrangements, right? So always be careful of rearrangements. So for example, if you have this alkene right here, and you try to add some HCl across it, first off, you're going to form your more stable carbocation, so you'll form a secondary carbocation here. However, this can undergo a hydride shift to become a tertiary carbocation. And then after that, the chlorine can attack to form your final product, right? So you're going to get a mixture of things here, which is, less desirable. And the general rule is if a carbocation arrangement can occur to form a more stable carbocation, it will.